some force, which I will call F2. Maybe it has some force, which I will call F3. And if we want to know where that box is going to move, it's not going to be in the direction of any of these forces by themselves. It's going to be in the direction of the cumulative effect. Okay? The cumulative effect is given by what we call the net force. Okay? This symbol here that looks like an E is the Greek letter sigma. It represents the sum. Okay? This is what we call the net force. And it's a vector. If both teams pull the rope to the right, the rope's going to move to the right. If both teams pull the rope to the left, the rope's going to move to the left. If both teams pull the rope in opposite directions with the exact same force, what does the rope do? Nothing. Doesn't move. Okay? You have to take into account the direction of these forces when considering their cumulative effect. Okay? So forces have to be given as vectors. They cannot be given as scalars. Their direction matters. Okay? When adding these forces, because they're vectors, we would not be doing a simple scalar addition. It's not going to be like 3 plus 4 equals 7. Okay, there's going to be a special form of addition for vectors that we're going to talk about in a little bit. Okay? In order to do this addition of vectors, like I said, we're going to have to convert the information from magnitude and direction into components. Once we have the components, we can do the addition of 1, 2, and 3 to find the net force. That net force will be in components. We'll know the x component of it, we'll know the y component of it. If we want to know where this box is going to move, we need to find the direction of that net force, so we have to convert back from component to magnitude and direction form. Okay? This is a very, very prototypical kind of calculation that we'll do. You start with information in magnitude and direction form, you break it down into components so that you can do the algebra, and with the answers you convert them back into magnitude and direction form. Okay? Any questions? Okay, so let's see how to convert backwards. Let's imagine that we did the sum, and let's say that we found that our vector has components. Ax is 3 and Ay is 5. Okay? Before trying to find the magnitude and direction, we should first draw this vector in an xy coordinate system. Okay? Before doing any vector math, you should always draw it. I started by drawing it here. I'm going to start by drawing it here. Okay? All we need to know are the components to determine roughly where that vector is pointing. We won't know exactly what angle it's pointing at, but we'll know roughly where it's pointing. Okay? Because it tells us that the vector is 3 ticks to the right and 5 ticks upward. So the vector is going to point roughly like this. Okay? I can draw a picture just like I drew here, where I can say that how far this vector points along the x-axis is the x component, which we know, and how far it points along the y-axis is the y component, which we know. And the hypotenuse, once again, is the magnitude, and that forms a right triangle. Okay? The exact same right triangle we used here, it's just now we know different information. Okay? So this is A, this is theta, this is AX, and this is AY, and here's a right angle. How would we find the magnitude if we know the components? Pythagorean theorem, right? All you have to do to find the magnitude is find the hypotenuse of this triangle, and the hypotenuse is given by the Pythagorean theorem. A is going to be the square root of AX squared plus AY squared. This will always be true. Okay? That's always what the magnitude is going to look like. You can always find it by using the Pythagorean theorem on the components.
Why would you put theta there? Just because?
Well, that's going to be the angle we're going to determine.
Okay.
We don't know what it is, but we're going to determine. Okay? So I can plug in numbers. The x component is 3. The y component is 5. So that's like 25 plus 9. 34, it's almost 6. Yeah, 5.83.
Formulas to find magnitude.
Yes, that tells you how long the vector is. Okay? Any questions about finding the magnitude of the vector given the components? Always going to be the Pythagorean theorem. That part's easy. Okay? The angle is a little bit trickier. Okay? And the reason that the angle is tricky is because you can choose a bunch of different angles to describe the direction of this vector. There is no one correct angle. Okay? When the angle is given to you in a problem, like it was in this problem, that choice isn't relevant because you're told what that angle is. But when you have to come up with the angle on your own, suddenly that choice becomes important. So let me redraw this vector a little bit bigger to illustrate what I'm talking about. Redraw it. Let's say that this is A. If I want to describe the direction of A, there are many different ways to do this, all of which are correct. They're all equivalent to one another. I could measure the angle starting from the x-axis and going counterclockwise. This is one possibility. Okay? That's the possibility that I chose here. This angle theta is in between the x-axis and vector itself. That's this one. But that's not the only angle you could choose. You could also choose this angle. That would be perfectly fine. There's nothing wrong with choosing that angle, it's just a different choice. You could also choose this angle if you wanted to. There's nothing wrong with that choice, it's just a different choice. Okay? You could also choose this angle if you wanted to, and many, many, many others. Yeah?
So if I choose whatever choice, would I still get the same answer?
No, the numbers are going to be different, but the numbers are all going to be related by simple geometry. The blue angle and the green angle have to add to 90. The blue angle and the red angle have to add to 180. Okay? The green angle and the orange angle have to add to 180. The orange angle minus the blue angle has to be 90. Okay? There are always these simple geometric relationships between the different choices. So it's not that any one choice is correct. They're all correct. Okay? You just have to choose one and get an answer, and then when you write your answer, you have to specify which particular reference you chose. Did you choose to reference it from the x-axis, the positive x? Did you choose to reference it from the positive y? Did you choose to reference it from the negative x or from the negative y? Those choices are all different because the choice of reference is different. Okay? But there is no correct choice of reference. They're all correct. Okay? In order to simplify this, I'm going to teach you guys one way of doing this. And as long as you always follow this one way, your answer will always be correct. Okay? It's a two-step process. angle to the nearest x-axis. What I mean is, if you think about the x-axis being split in half, there's a positive side and there's a negative side. Same thing for the y-axis. You can imagine splitting the y-axis in half. There's a positive side, there's a negative side. There are 4 choices here. The green choice is to the positive y, the orange choice is to the negative y. Neither of those are to an x-axis, so we don't want to use them. The blue and the red choice are to the x-axis. One of those two is going to be our nearest x-axis. Which one's closer, the positive x or the negative x? Positive. So you want to choose the blue angle. This is going to be your choice for step 1. You're always going to choose the angle to the nearest x-axis. This guarantees that your angle is always going to be less than 90 degrees. Okay? If your angle is ever greater than 90 degrees, calculators have trouble doing trigonometry because there are multiple choices for any angle that's greater than 90 degrees. Okay? If you want to restrict yourself to one possible answer to guarantee that that one answer is correct, you need to use an angle that's less than 90. Okay, I don't know if you guys remember this well from trigonometry, but answers repeat themselves in trigonometry. Okay? That's why when you solve like trigonometric equations, there's always like a dot 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 for your answer. Okay, when is cosine 1? It's 1 at 0, it's 1 at 2 pi, it's 1 at 4 pi, it's 1 at 6 pi, etc. Okay? There are all of those possible answers. The same thing comes into play when you're trying to do trigonometry on your calculator. If you guarantee that your angle is less than 90 degrees, there will always only be one correct answer. Okay? Step 2, because you chose your x-axis to touch your angle, the x-axis is always going to be the adjacent, and we'll use tangent to find the angle. We'll use tangent because we'll know the x and the y, so we'll know the opposite and the adjacent. Tangent has to do with opposite and adjacent. So if you always choose the angle to the nearest x-axis, the angle will always be given by the formula. Theta is the inverse tangent of the absolute value of the y component over the x component. Okay? So right here, for my vector, if I choose theta to the nearest x-axis, which is the positive x-axis, that's my angle theta. Theta is going to be given by the inverse tangent of the absolute value of y over x. The absolute value is not relevant in this problem because both are positive, but it will be relevant in some problems. I'll show you an example in a second. So it's tangent inverse. The y is 5. The x is 3. Which is 59 degrees. There's your magnitude and your direction. Vector A has a magnitude of 5.83 and it points at an angle of 59 degrees above the x-axis. Okay? You can also say that that's counterclockwise measured from the x-axis, however you want to say it. 59 degrees above the x-axis.
It has to be written out like that sometimes?
Yes,
Like
sometimes it
word
will
form?
have to be written out.
Okay.
Okay? Yeah.
Those indicate that it's an absolute value, right?
The bars, yes.
Yeah, okay. So just
Okay.
because we didn't have a negative sign, you just put it brackets.
Exactly.
Okay.
Any questions? Let's see another example, one where the vector will have a possible negative sign, or one where a vector does have a negative sign in the components. So some vector B has components, bx is 4, by is -1. Okay, let's start by drawing this vector. Here's x, here's y. It extends 4 in the x direction, and it extends -1 in the y direction. Another way to think about that is it extends 1 in the negative y direction. So I can draw the vector like this. Here's the x component. It extends 4 out in the x direction. And then here's the y component. It extends 1 in the negative y direction. Okay? And that forms the vector b. Okay? How will we find the magnitude of b? Pythagorean theorem, right? Always the Pythagorean theorem. Okay? So the magnitude of b is always going to be the square root of the x component squared plus the y component squared. Something to always recognize is that this y component is negative, but when you square it, it will always be a positive number. Okay? This will always be a positive sign. It will never be a negative sign. Okay? The y component is negative, but when you square it, that -1 becomes positive 1. So you can just write it as 4 squared plus 1 squared. You don't have to worry about the negative sign. So that's 17, square root of 17 is 4.12. Okay? That's its magnitude. Any questions about its magnitude? All right, now the angle, once again, we're following this two-step process. Always choose the angle to the nearest x-axis. In this case, the nearest is still the positive x. So this is going to be theta. Okay, and then we'll always use that formula, the inverse tangent of the absolute value of y over x. So theta is going to be the inverse tangent of the absolute value of the y component over the x component. Okay? What's the absolute value of the y component? Positive 1, right? The absolute value is just a positive number. What's the x component? 4. That's 14 degrees. So we can say it's 14 degrees below the x-axis. That b starts out along the x-axis and it points 14 degrees below it. Yeah?
Are you always going to round to the nearest degree?
You know, it's up to you. I chose to in this case. Remember that the test will be multiple choice. So you'll just choose the one that reflects what your calculator shows. I'm not going to say like 14.1 degrees or 14.2 degrees. I'm not going to be that close. So possibilities might be like 14 degrees, 35 degrees, 60 degrees, 72 degrees, something like that. They'll be spaced apart. On mastering physics, it's going to want a certain number of digits, but which number of digits it wants depends on the question. So when in doubt, you can always just write 3 digits. So in this case, it would be to 1 decimal place. Okay, and sometimes you have to like fight with mastering physics to get it to accept your answer.
Oh my gosh.
Yeah, it's the best option out of, it's pretty good software. Everything else sucks. Physics questions are really, really, really hard to test online because they involve a lot of like logic that computers can't replicate. It's not like math, where math is always going to follow a set series of steps. When you ask a question in physics, there's no set series of steps to always follow to get the answer. So it's really hard to write computer software to test people on physics. Okay, mastering physics is by far the best out there. Okay, but it still has its issues. Any questions?
one would be to find which term?
The
vector?
direction.
The direction.
This is the
one's
direction.
magnitude.
Yep. Let me do one more really quickly. Some vector C has components. Cx is -2, Cy is -3. I'm not going to worry about the magnitude. The magnitude is easy. It's the Pythagorean theorem. Square root of, it's 2 squared plus 3 squared, square rooted. Let's only worry about the direction, because that's the more difficult choice. Always start by drawing your vector. The x component extends in the negative x direction. So Cx is going to go to the left. The y component extends in the negative y direction. So Cy is going to go down. And the vector C is going to point like this. Always draw the angle to the nearest x-axis. In this case, which one's the nearest one? The negative, right? Not the positive. The positive is going to require looping like this, and it's going to have an angle greater than 180 degrees. We want an angle less than 90. Okay? So you're going to choose this angle to the negative x-axis, and theta will be given by the tangent inverse of the absolute value of the y over the x. Okay? Tangent inverse, the absolute value of the y is 3. The absolute value of the x is 2. 56.3. Okay? And this one is below the negative x axis. It's a perfectly valid way of describing that angle. Something to bear in mind is that you have complete freedom to choose whatever reference point you want. And I told you a convenient reference point to choose. That way you're guaranteed to do the trigonometry correctly. Trigonometry can be funky when working in the quadrants that are not quadrant 1. Quadrant 1 is this one, where both are positive. Trig is very easy to do in quadrant 1, but it can get weird in 2, 3, and 4. So to avoid that, if you always choose the angle to the nearest x-axis, the trig will always be very easy and very straightforward, because your angle will always be less than 90. Okay? Now, on mastering physics, it doesn't have the flexibility for you to choose your reference point. Mastering physics will tell you what reference point to choose, and it might not be the same reference point as the convenient one that we use. So worst case scenario, you have to do a little bit of geometry to get the answer in the form that mastering physics wants. Okay? Mastering physics typically asks for angles to be measured counterclockwise from the positive x-axis. So starting from the positive x, measuring counterclockwise. Okay? That is not that angle that we found for vector C. But we can find that angle from our answer. So this is vector C, and we know that our answer here, theta, is 56.3 degrees. Mastering physics might ask you to give the direction of C measured counterclockwise from the x-axis. So starting at the x-axis, going counterclockwise is this angle. If we know that theta is 56 degrees, how do we find the blue angle? Add it to 180. This is 180 plus 56. I'm terrible at arithmetic, so I think that's like 236 or something. Yeah. 236 degrees. So there are two perfectly valid ways to describe the direction of this vector. They are both correct. Our convenient way to describe it is 56 degrees below the negative x axis. Okay, instead of saying below, we could say counterclockwise to the negative x axis. That's a perfectly valid way of describing the direction of this vector. Another perfectly valid way is to say 236 degrees counterclockwise to the positive x axis. The numbers are not the same because the reference point is not the same. Okay, but they are both correct.
So when you say counterclockwise, you automatically mean below x-axis?
No.
Okay.
I just mean counterclockwise in the sense of a circle. Okay, in this case, below means counterclockwise. In this case, below actually means clockwise.
Right.
Okay, that's why drawing pictures helps. Yeah.
On your test, the answers will be according to.
Yes, but I'm going to follow the convention that I told you guys. So as long as you follow my method correctly, you will be able to get the easy answer that I chose on the exam. But no matter what, you can always do these conversions. These conversions are simple geometric problems. Okay? Any questions? The goal is not necessarily to come up with the simplest way to get the answer, because my method's not the simplest way. The goal is to get a way where you will consistently get the right answer. My method takes a little bit more work, but it eliminates the ambiguities in the tangent function, and you will always get the right answer if you do it this way. Just takes a little bit extra work. Yeah.
So you're just trying to find data.
Yeah, just trying to find the direction. Okay? But that's the thing, is that direction is not a quantity that you can just give without some reference. Okay, I can't just say that C points at 56 degrees. 56 degrees from where? Okay, and that choice of reference is flexible. And because it's flexible, there are multiple correct answers. Any questions? All right, so now let's talk about how to do algebra. There are 4 vector operations, just like there are 4 scalar operations, but they're slightly different. Okay? There's vector addition. If you add 2 vectors, you get out a third vector. So the vector A plus the vector B is a third vector, C. Something that's important to note is that when I'm talking about vector algebra right here, I'm talking about using 2 vectors to do the algebra. We have 2 fundamentally different types of mathematical quantities. This is the first time in your entire life that you actually, you guys have dealt with matrices before, probably, in like high school. So matrices were another example where you dealt with a fundamentally different type of mathematical quantity. Okay? You could not add matrices to simple numbers. There is no such operation as like 3, 1, 0, 1 plus 4. This is not a possibility. Okay, you can only add matrices together. Okay, the same thing is true for vectors. If you want to add them, you need to add 2 vectors and you get a vector out. Okay? Same thing for subtraction. vector subtraction. You subtract two vectors, you get a vector out. A minus b is going to be a new vector, d. Okay? It turns out, though, that the difference between vector algebra and scalar algebra is that there are two types of vector multiplication, and there are no types of vector division. Okay? For scalar algebra, there is one type of multiplication and one type of division. For vectors, two types of multiplication, no types of division. Okay, we differentiate between the two by the symbol that we use. So one of these is called the cross product, and one of these is called the dot product. When you are writing out scalar multiplication, there are two symbols that can be used to describe multiplication. One of them is a cross, like an X, and one of them is a dot. When you guys are learning arithmetic back in like elementary school or whatever, you typically use a cross for all arithmetic operations, like 3 cross 4, or 7 cross 1, or whatever. Okay? But when you get into algebra, X becomes a variable, and to avoid that ambiguity, you switch from the cross to a dot. Okay, but this is equivalent to 3.1. This is equivalent to 7.1. That is not true for vectors. For vectors, we have two multiplication operations, and we distinguish them by using different symbols. So the cross product is written as A cross B, and the dot product is written as A dot B. And those are distinct operations.
Oh, so they're not.
They're not the same. The major important difference right now, the most important thing for right now, is that the output of the cross product is another vector, but the output of a dot product is actually a scalar. It is not a vector.
Is that a lowercase d?
Yeah. Okay? It's important to recognize that a cross product outputs a vector, a dot product outputs a scalar. Okay? They are used to accomplish different things. And I'll give you guys a demonstration that will hopefully illustrate the two different applications, the cross product and the dot product. But we will use these different operations to accomplish different goals in the study of physics. Until we really discuss physics in depth as the class goes on, this math is probably not going to have very much meaning. But as we study physics more and more and more, and you see the cross product and the dot product actually used to describe real things in the world, hopefully they will have some sort of like intuitive understanding for you guys. Okay? First, let's talk about how to do these operations though. One of the benefits of breaking vectors down into their components is that when you do algebra, the components of vectors are themselves scalars. So scalar algebra is actually going to look almost identical to, vector algebra is going to look almost identical to scalar algebra. Okay? We'll borrow all of the rules from scalar algebra to build the rules for vector algebra. And that's because we write out vectors as just a list of numbers. Okay? I want to talk a bit about notation really quickly before we continue, because for right now, we haven't talked about a convenient way to write out a vector. So far, every vector that we've encountered, I've written out as a sentence. Okay? Now that we're starting to do math, I want a compact way to describe vectors. I don't want to have to write out a sentence every time I need to describe a vector. Okay? The notation that we're going to use is going to be a notation for the component forms of vectors. The magnitude and direction forms of vectors it doesn't really have a compact notation. When you're describing the magnitude and direction of a vector, you will either draw it as an arrow in a picture, or you will write it out as a sentence. Okay, those are the two most common ways to give a vector a magnitude and direction form. But as far as talking about components, there is a compact mathematical notation for the components. Okay, and those use these things called unit vectors. Okay? When I said the vector C has components, I don't remember what I wrote. Cx is, let's say, -2, Cy is 4. It doesn't really matter. Those numbers just tell you how far the vector points in each of the two possible directions. To grab this information and write it out as a vector, we need to somehow tag the number 2 with something that tells you that it points in the x direction. And we need to tag the number 4 with something that tells you it points in the y direction. The general idea is that vector C is going to look like -2 plus 4 that way we know not to combine these two numbers. We need some way of separating those two numbers. Because if we add those two numbers, -2 plus 4 equals 2. 2 is a number that has nothing to do with the vector C. The vector C's magnitude is not 2, neither of its components are 2. So if you do 4 minus 2, you get a number that's irrelevant. So we need something here to tag these numbers so that we keep them distinct. We keep them separated. Okay, and we use the concept of these unit vectors to do this. What a unit vector is it's a vector that points in a predetermined direction that everybody agrees on that has what's known as a unit magnitude. A unit magnitude is a magnitude of 1. So one of our predetermined vectors points in the x direction, and we call it I hat. Okay, sometimes it's called x hat. Okay, the hat is the symbol that we use specifically for a unit vector. We don't put an arrow over them. An arrow goes over a vector that has any length. A length of 5, a length of half, a length of 17. When you put a hat over a vector, you're specifying that it has the specific length of 1. And I'll tell you why that's important in a second. Okay? Then in the y direction, we have the unit vector j hat. Okay? The z direction, if we have a 3-dimensional coordinate system, it's described by a unit vector k hat. Physics is built on the language of math, but mathematicians and physicists are like cats and dogs. They have chosen to constantly butt heads over everything for the entire history of the endeavor, from roughly the 1600s. So mathematicians will use the notation I, J, and K, and physicists, because they have to be different from mathematicians, will like to use the notation x hat, y hat, and z hat. Okay? I don't remember which notation your book uses. The more common notation is the mathematician notation, I, J, and K, but they're equivalent. Okay? So
They
if
all
you-
have a hat.
Yes, they all have a hat. So I hat can be given instead by X hat. J hat can be given instead by Y hat, and K hat can be given instead by Z hat. Okay? But notice that I, J, and K are 3 letters in a row, just like X, Y, and Z are 3 letters in a row. Okay? All you have to do is take these numbers that describe the components and multiply them by their corresponding unit vectors. The reason this works is because there is one operation between scalars and vectors. When I wrote down these operations, notice on the left-hand side, it's always 2 vectors. Vector A plus vector B, vector minus vector, vector times vector, vector times vector. There is only one operation where you can mix vectors and scalars. Okay, you can't add a vector and a scalar. You can't subtract a vector and a scalar. You can't do a cross product of a vector and a scalar. You can't do a dot product of a vector and a scalar. There's one operation, and that operation we just call scaling. That's where scalars get their name. This is the single operation between a vector and a scalar. If you have a vector that points in some direction and has some length, multiplying that vector by a scalar will change the length of that vector. A scalar will scale the size of a vector. So if you take A and multiply it by 2, you will get a vector that points in the same direction that is just twice as long. If you take A and multiply it by 3, you get a vector that points in the same direction, but is 3 times as long. If you take the vector A and multiply it by half, you get a vector that points in the same direction as A, it's just half as long. The one exception to this rule is if you multiply a vector by a negative scalar. A negative scalar can reverse the direction of a vector. Okay? No scalar can rotate a vector. So if A points to the right, no scalar can make it point 10 degrees above the right. That's impossible. But the one thing that a scalar can do is if you multiply it by a negative number, it can point to the left. Okay? So if I take A and I multiply it by negative A, I get a vector of the same length in the opposite direction.
Right.
If I take A and I multiply it by negative 3A, I get a vector that's 3 times as long in the opposite direction. So when I take my vector C and I say that C is composed of negative 2 times I hat plus 4 times j hat, what I'm telling you is you take a vector with a size of 1 pointing in the x direction, you make it twice as long, so now it's 2 units long, not 1 unit, and you point it to the left. That's exactly how far C extends to the left. It extends 2 units to the left. Okay? If you take the vector j hat, it has a size of 1 and it points up, and C is 4 units up. Yep.
For 2, I do flip back this way.
The negative flips I to the left, not the 2. The 2 just makes I twice as long.
To the left or to the right?
It makes it point in the opposite direction. X is traditionally written as pointing to the right.
Oh, okay.
So when you multiply it by a negative sign, you would say it points to the left.
Oh, okay.
Okay.
Because it's not the 2,
It's not the 2, it's the negative sign that flips it. Okay? Positive scalars don't change the direction of the vector, they just change the length of the vector. It's the negative sign that changes the direction. Okay, so all that this notation tells you right here, what this tells you is that C points 2 units in the negative x direction and 4 units in the y direction. This, by the way, is why you want to use unit vectors. You want them to start out with a length of 1. That way the components can remain the same numbers. What if I didn't use I with a magnitude of 1? What if I used it with already a magnitude of 2? Then this vector points 2 to the left. All I would have to do is multiply it by -1. So it would be -1 I hat, which would be weird. You want the number to match the component. Okay? So you build the vector out of these smaller vectors that have a predetermined direction. Everybody agrees that I hat points in the x direction and j hat points in the y direction. So those pre-chosen coordinates are fixed. You don't worry about what they mean. And you build your vector using those pre-selected directions. They both have a magnitude of 1. They're both unit vectors all the time, every time. Okay?
Every time for
For everything. Every single vector you're going to break down into these unit vectors so that you can read off their directions simply. All that this tells you is that when you draw your coordinate system, C points 2 units in the negative x direction, so it's -1, -2, and it points 4 units in the positive y direction. Okay? That's what C is going to look like. Okay? So this is a compact notation to contain all of the information about the vector. And it contains it in the component form. It doesn't contain it in the magnitude and direction form. This is specifically for the component form. Yeah.
These units are just a formality, right? So it's just basically to let us know that this is a x unit or y unit.
Yes. It's a more convenient form than writing the vector out as a sentence. This sentence here contains identical information to this compact statement. This equation here is just a compact form of this sentence. Okay, and it allows for you to do math more easily. Any questions? All right, so let's actually do addition. Now that we have this notation out of the way, let's see how vector addition works. Like I said, we're going to borrow the rules for vector addition. We're going to borrow them from the rules of scalar addition. Imagine that we have a vector A, which is -I hat plus 3j hat, and we have a vector B, which is 4I hat plus 2j hat. What will A plus B look like? The first thing that we're going to do is we're going to plug in our vectors in component form for the symbols A and B. So A becomes -I plus 3j, and B becomes 4I plus 2j. Okay? All you have to do now is group like terms. Okay? You should think about the I hats and the j hats as independent variables that cannot be mixed. From regular algebra, if I told you that you guys said 3x minus y plus 2x plus 4y, how would you simplify this expression?
Just 5x
5x
plus 4y minus 3y. I mean
plus
plus
3y.
3y.
You guys have the general idea. You
Yeah.
group the x's, you group the y's, but x and y don't group themselves. They stay separate.
Right.
Same thing happens with these unit vectors. You group the I hats together and you group the j hats together, and it follows the regular rules of scalar addition. What is -1 plus 4? Scalar addition tells us 3. So this first term becomes 3I hat. What's 3 plus 2? 5. and that's it. Just borrow the rules from scalar addition.
That's the answer.
That's the answer. That's A plus B. Yeah.
Are you ever gonna ask us to write this in magnitude direction form?
It could. It could ask you, what's the magnitude of A plus B? What's the direction of A plus B? So what we'll do is we'll take our answer and we'll convert it into magnitude and direction form. Okay? So let me draw this problem out. I'm gonna come over here and I'll draw it with space. X, Y. A points -1 in the x direction and 3 in the y direction, so A points somewhere like this. B points 4 in the positive x direction and 2 in the y direction, so B looks something like this. Okay? When we added those two together, we could call this vector C, and it points 3 in the x direction and 5 in the y direction. So C equals A plus B looks something like this. Question is, what's the magnitude of C and what's the direction of C? Magnitude is always going to be found by using the Pythagorean theorem. What's the x component of C?
3,
What's the y component of C?
5.
5. So C will have a magnitude of the square root of 3 squared plus 5 squared. 9 plus 25, which is 34. 5.83. And how will we find the direction of C? Always choose an angle to the nearest x-axis, which is this x-axis here. And theta is always going to be the tangent inverse of the absolute value of the y component over the x component. Y component of C was 5. The x component of C was 3. That's 59 degrees. We measured it from the x-axis, and the angle points counterclockwise.
That's the direction, right?
Yep. That's how you would find the direction and the magnitude of C. So remember, after doing algebra, C is going to be given in component form. If you need to find the answer in magnitude and direction form, you need to convert.
I thought the magnitude was 1, that's what I got.
No, the unit vectors, the I hat has a magnitude of 1.
Okay.
So what's the magnitude of the whole piece? If I has a length of 1 and you multiply it by 3, what's the length of it? 3. If J has a magnitude of 1, it has a length of 1, but now up, and you multiply by 5, what's its new length? 5. So you have a vector that points 3 in the x direction and 5 in the y direction.
Gotcha.
Okay? Notice that C is not a unit vector, and I don't give it with a hat. There's no reason to believe that C is a unit vector. So I don't put a hat over it. Okay, the unit vectors are I and J, and K if there's a Z direction involved. Yeah,
What is CCW?
counterclockwise.
So this is how you want us to solve it, like a full question like this?
If the question involved that, then yeah, this is how you would solve it. I don't have to ask this many things. Maybe I only ask you what A plus B is, and the answer is in component form. Then 3I plus 5J is the answer. But if I ask you for A plus B, and I ask for the magnitude and the direction of it, 5.83 is the magnitude of A plus B. And the direction of A plus B is 59 degrees counterclockwise from the x-axis. Okay? Any questions? Yeah.
You wanna find the magnitude of C,
No, I just drew them there to show that C points in a different direction and it has a different magnitude. So C is not going to share the magnitude of A, it's not going to share the magnitude of B. The magnitude of C is not the sum of their magnitudes. It's not. What's the magnitude of A? We can use the Pythagorean theorem here. A, this is 1 squared plus 3 squared, which is 9. 9 plus 1 is 10. Square root of 10 is 3.16. So the magnitude of A here is 3.16. B, Pythagorean theorem is 4 squared, which is 16, plus 2 squared, which is 4. 16 plus 4 is 20. The square root of 20 is 4.47. So the magnitude of B is 4.47. The magnitude of C is not the sum of the magnitudes of A and B. Okay, these are not scalars.
Okay.
You cannot say that C equals A plus B. It will not be true that the magnitude of C is the magnitude of A plus the magnitude of B. This is not true. Sorry, that statement is true. The not equal, okay? It being equal is not true. All right? These are not simple scalars.
So why do they write it like that if it's not true?
No, this statement is true.
Right.
This is the vector C equals the vector A
Okay,
doing
got it.
vector addition to the vector B. That's true.
Okay.
But saying that the magnitude of C is the magnitude of A plus the magnitude of B, that's incorrect. Okay? You cannot just add their magnitudes. The magnitude of A is 3, the magnitude of B is 4.5, the magnitude of C is 6. Those numbers don't add up. Okay? Someone else raised their hand?
Yeah, it's
Yeah.
always.
Okay. Any other questions?
So when it has the absolute value thing on the side, that just means magnitude?
Yeah, that's another way. You could also write it as just C not equal to A plus B. But the problem here is that now these sort of look like scalars.
Right.
I wanted to be explicit about it. Okay? Any other questions?
Wouldn't we have to get use the cross product and we'd get the same result, but we don't, right?
No. Cross product's a different thing. Cross product's a type of multiplication. It's not a type of addition.
But wouldn't we get the vector of C?
Oh, sorry. No. That's just the notation.
Oh,
I should have written the third vector like F or something.
Oh, okay.
No, when I wrote out this here, I didn't mean to imply that this C and this C were the same. Okay, you can call this like F, and you can call this like G. Okay, I just wrote the same letters again. I didn't mean to imply that this and this were the same.
So is that what you're basically saying over there?
What?
That's what you're basically saying over there?
No. Over here, all I'm doing is the addition. I haven't done anything related to the cross product yet. Okay? All I asked here was, what is the vector sum of A and B? This is it in component form. This is it in magnitude and direction form. And now I'm just illustrating different properties of the addition. For instance, that the vector addition of A and B does not, the vector addition is different than the scalar addition. Okay? The vector addition of A and B does not imply that the sum of the magnitudes equals the magnitude of C. I'm just illustrating properties now. Okay? Any other questions? I'm trying to show you guys that vectors are different than scalars. Okay, so if I tell you A has a magnitude A equals 5 and points 30 degrees counterclockwise from the x-axis. B has a magnitude of 2 and points 20 degrees counterclockwise from the negative x-axis. What is C equals A plus B? Okay? What I'm trying to tell you is that if you want to find the magnitude of C, you cannot just add 5 and 2. That is not the magnitude of C. The magnitude of C is not 7. Okay, before you can do the vector addition, these vectors A and B, which are in magnitude and direction form, you must convert them into component form. So the first step is to convert them into components. Once they're converted into components, you can add them, and you will find the components of vector C. Once you know the components of vector C, you can then find the magnitude of vector C and the direction of vector C. Okay, I'm not going to go through the whole process of answering this question because I've already answered every single piece in that problem. All right? Any other questions? You guys can do this on your own and see if you guys can get answers that are consistent. And by the way, there are probably like vector calculators online that will confirm whether your answer is right or not. Okay? Any questions? Let's do subtraction. Once again, subtraction is just going to borrow from what we know about scalar subtraction. A minus B. I'm going to use the same two vectors here. Plug in A is negative I plus 3j minus, plug in B is 4I plus 2j. What do you guys think you're going to do from this point? What feels natural? Yeah, so
Same thing.
what's the answer going to be? What's the x component?
-5.
-5. How'd you get -5?
Add negative to the 4.
Yeah, you're holding the negative sign into the parentheses, right? You are distributing the negative sign. What about the y component? What are you going to get? 1, right? Because you're distributing this negative sign. That's a rule from scalar algebra that we borrow into vector algebra. So this 4i becomes negative 4i, and negative 1 minus 4 is negative 5. This 2j becomes negative 2j, and 3 minus 2 is 1. Okay? Any questions? By the way, in your guys' notes, I just realized you should make a point because of how it's probably writing as a flow of the information I'm giving you. I wrote this down and I immediately went back to here. These numbers don't correspond to this question. This question I wrote for illustrative purposes. These numbers correspond to these previous numbers which have nothing to do with this question. So you should make sure to like box off this question or something in your notes and make sure that it's like an aside. It has nothing to do with what we were talking about here. Okay, just so you guys don't get confused. That way you're not like, hey, where's this -1 plus 3 from? That has something to do with this vector. Okay, these two things are separate. Or there are only so many letters. Okay, I'm gonna use like A, B, and C a lot. Any questions? All right. We can combine now the idea of addition and subtraction with the idea of scaling, which I had introduced before. What would 2a minus 3b equal? 2a is the scaling of the vector a by 2. Negative 3b is a scaling of b by negative 3. So let's plug in our vectors. 2a is negative I plus 3j minus 3. b is 4i plus 2j. Where do you think you go from here? You distribute the 2 into A, and you distribute the negative 3 into B. Okay? This scaling operation, this idea of taking a vector and changing its length by a scalar, it follows the regular distributive property that we know from scalar algebra. You just multiply this 2 into here, multiply this negative 3 into here, this becomes negative 2i plus 6j minus 12i minus 6j. So it turns out the j's cancel, and this is just negative 14i. Any questions?
So this part right here that you just completed, there's no scaling in that, that's just vectors, is that right?
No, this 2a minus 3b, this does involve that scaling operation.
Oh,
So
okay.
you're taking a and you're doubling its length.
Oh, oh.
So if I were to draw this, if I were to have a, which I said pointed like this, and I were to have b, which I said pointed like this, I wouldn't use these vectors to do my subtraction. Or really a subtraction looks the same as addition. This is the same as 2a plus negative 3b. I would take a and I would double its length in the same direction, and that would be the vector that I use. B, I would triple its length and reverse its direction. And this is the vector I would use. I would add these two vectors together, and that would give me C, or whatever else I called it. Okay? But instead of doing it graphically, like I drew it, we're doing it algebraically. We're doing it with numbers.
So I was gonna ask you, what happens when you don't have a J? You only have the 14i.
All that tells you is that 2a minus 3b points to the left. Straight dead left. It has no upward component, no downward component. So it's telling you
So
that
you would write it like,
it would look like this.
would you write it like counterclockwise from x-axis?
Sure, you can write it as 180 degrees counterclockwise from the x-axis if you wanted. Or you could just say left.
Okay.
This is 2a minus 3b. It's just 14 units to the left.
Oh, okay. Duh. Okay, got it now.
Mhm. Any questions? There is a graphic way to determine the sum of any vectors just by using these pictures. The graphic way is called completing the parallelogram. And this will be the last thing that I mention really quickly. This is not a reliable way to get numbers, okay? This is just to get qualitative information out of it. By looking at this picture, I can tell that C points somewhere to the left, but I can't get the information that C points dead left with no vertical component at all. Completing the parallelogram is a graphic way to do vector addition. Once again, it's not reliable. It's just to get some qualitative information out of it. So if this is A, and this is B, okay, like I said, if I wanted to do 2A minus 3B, I could double A to be 2A. I could triple B and draw it in the reverse direction. This would be negative 3B. And then what you imagine is that A and B, or 2A and negative 3B, are two pieces of a parallelogram. Okay, a parallelogram is a quadrilateral where opposite sides are parallel. So these two edges are parallel, same length. These two edges are parallel, the same length. So what I would do is I would imagine taking this negative 3b and drawing it from here. Okay? This looks the same as negative 3b. And I would imagine taking